So I've been struggling with DCC and DECO model, but I think a very small, what should I say, very small memorizing of stuff will make things easy. So we're gonna go into DCC model one more time, keeping in mind what we have learned up until now. First, we need to specify the GARCH 1.1 model, then the correlation component R, because that is important for DCC, and we need to find the full log likelihood function for DCC model, and the full log, we're just gonna go through the question one more time, or before that. So correlation component and the full log likelihood function. The theta 2 is the correlation parameter, and theta 1, theta 2 need to be estimated. So GARCH parameter is a volatility parameter or GARCH parameter. When we solve log likelihood function equals 0, then theta 2 parameter for correlation component, and the unknown parameter is 3n plus 2. That is something we need to remember. And this is the GARCH parameter code. R is the correlation component, as we know. We were reading this already. So I'm just gonna go through very quickly one more time, and let's see if it makes sense this time. So this is your function where your residual is y, right? And when you are looking into normal cumulative distribution function, you're doing it for high dimensional input, where you are looking for a bound, right? A covariance bound. Basically, you ask this function to give you mean, mu, standard deviation, and peak of, or the covariance matrix. So let's first, standard deviation will be alpha naught, beta 1 indeed, which is constant. Then we have mean multiplied to y squared, beta 2, whatever beta 2 will be. You see this is stocked u square, stocked. Is multiplied to the residual, okay, that is your mean parameter. Variance is standard deviation of, this is something we need to memorize, that's all. Standard deviation of v square, and we want norm CDF for beta 3 variance covariance matrix, which is, in case of a single norm CDF, it should give me okay, this is already there. So in case of a single norm CDF, a single input, where it returns the standard normal cumulative distribution function at each value in S. Sigma can be vector, matrix, or multidimensional array. So x mu and sigma, x mu and sigma, not mu sigma, I'm sorry, x mu and sigma. So this is x, which I'm estimating, mu. Also this is x, which is residual, x. Mu is u square, standard deviation of u square. Sigma is variance, and it gives me standard normal cumulative distribution function. Confidence bounds are estimated x minus mu by sigma. It's cumulative distribution function, that is cumulative distribution function simply stated. Confidence bounds for p using a normal approximation. Norm CDF estimates confidence bounds. Okay, so this will be sigma. This is mu, which is u square. This is x into trimar or something, b2 into trimar. So z gives you u by, we already know it, we already know this equation. Correlation should be same as well. B is again x, normal cumulative distribution function. Just memorize it. T rows, column size of y, where the t rows, number of rows are selected in t, 0s t1. So just select, we're just setting things to motion. Y equals u So y square is mean. Y square is mean. Is there any other way to define this? Probably yes. X mu peak of alpha. Okay, fine. So z is equal to this, then q bar is, as we have learned before, S is diagonal. So now this shouldn't be that difficult. Basically this is the part we need to memorize. And then q bar is ZZ transpose divided by T, which is q bar, and we know where q bar comes into the GARCH equation. We will use it into the GARCH equation. S is diagonal of q inverse. Then we use S. Well, q is q bar, and ZZ transpose divided by T. We have used them already. ZZ transpose, we have gone through that. There you go. This is coming from this equation. ZZ transpose divided by T is q bar, right? So let's go into q bar. Yeah. Looking into this, we find R with that information. Inverse of diagonal q is where the standard deviation is located. So we take R and we find the function that is given to us. Then we update q in GARCH. So that's easy. We have done those equations. I'm not sure why we are initializing with these random numbers. Anyway, just memorize this part. Then we construct conditional variances. This is construction of conditional variance. With the previously same equation, we find conditional correlation, diagonal matrix, and then we update SRS. This is the actual equation that we had based on function q and log function. Now let's see the main body of the program. So we bring in quite a lot many data this time, and then we optimize the data because it's 3n plus 2. So B1 is 3 rows and columns, ST is 3 rows and columns, because we probably have is 3n plus 2 is the formula. We'll follow that. For in a loop we find neg log GARCH. For all we find the standard deviation, we find the beta coefficient, GARCH parameter. So these are the GARCH parameters are located in B1. Fine. And then we estimate correlation component, and after estimating the correlation component, we run optimization, and beta 1, BC, BF, we find them. Now what about DECO model? Let's have a look into the DECO model. DCC model is extremely difficult. The question is how difficult DECO model will be. It's a dynamic equicorrelation model of Angel and Kelly in 2009. It is the unconditional correlation matrix of system of financial returns. The correlations of DCC model are therefore assumed to be equal contemporaneously across all n variables. So is across variables they're equal, but not over time. They are not time varying. So the returns are equal across the variables, but not over time. So average represents the average of nn minus 1 by 2 correlations at time n, 2 by nn minus 1. The advantage of DECO restriction on the correlation matrix is that as n increases, it becomes relatively easier to maximize the log likelihood function of DECO. Rewriting these restrictions, we can basically start with zeros and ones. identity matrix and zero matrix. 1 minus R identity, R0, where I is the identity matrix, I is then ones. This form, the correlation matrix R, has the following analytical property. 1 plus R is 1 minus R n minus 1, 1 plus n minus 1 R. So this is something. Let's see how DECO model is implemented in our problem. So let's start with the functions in DECO model. Again, U equals I rex RR. We just memorize it. We memorize U square divided by H square. Log likelihood report function, because log function returns the average. Log likelihood function, fine. Log likelihood report function. Neglect DECO. B is again with norm CDF. Residuals, standardized residuals. Then variant Q bar, diagonal matrix, just exactly same as before. Conditional correlation, just compute mean of covariance. Vic trill R minus 1 something, I'm not sure what this is. Vic is vectorization. Trill R minus 1, trill is a function. Okay, trill is triangular representation of R minus 1, which equals 0. I'm not sure if trill is there. Lower triangular part of matrix. Trill X, trill ones 4 4 minus 1, 4 4 minus 1. Okay, makes sense now. Lower triangular R minus 1, which is equivalent to 0. So ones are located. So it gives you something like this, right? In zeros, in the lower triangular part you have ones. Something like that is R. Is it R? No, this is index R bar, mean of R int. Okay, redefine R for DECO. 1 minus R bar. Okay, 1 minus R bar, that is R bar. Lower triangular, take the lower triangular. 1 minus R bar, n minus identity plus R bar into ones. Good, this is the equation. Determinant and inverse of R for DECO. 1 minus R bar n minus 1. This is the equation. 1 minus R bar n minus 1. Exact same equation. R determinant and R inverse. Log of likelihood observation. R inverse Z, R inverse Z. Very simple, though it's not mentioned, but yeah. Update Q just as before. So beautiful, easy. Then log full, just like before. We find conditional covariances just like before. Then compute mean just like before. Redefine R and update conditions. So these are the additional information given in DECO, passed in DECO, and data is included. Then comes we start, we run the function, and we get the parameters. We get the GARCH parameters. Okay, beta 1 2 3, beta 1 2 3 is normal cumulative distribution function. 2 3 is actually alpha and beta. That's all. First of all, sigma, then alpha, then beta. Sigma, alpha, beta. Very simple. Okay, so that makes sense. So we are done with DECO and DCC. So there's quite a bit of memorization. We need to memorize a few things. Now comes DCC and DECO's application. We have seen the applications and they are quite a treat. A time varying volatility structural VAR model. Now this is something important. The following application uses an S VAR model with short run restriction testimonial model for 3-month UK labor rate. The data are for the period. An important feature of this model is an allowance for structural shocks to have time varying. Any problem? for structural shocks. To have time varying conditional volatility, they have a alternative method. So this is an alternative method. Structural VAR model is an alternative method and it's a highly applied method. Okay. Let Y contain the following 6 variables. The VIX index, which is a measure of volatility constructed from European put and call option prices, such that at any given time it reflects the risk neutral expectation of the integrated variance average over the next 30 calendar days or 22 trading days. The VIX index is a measure of volatility constructed from the option prices. It reflects risk neutral expectation of the integrated variance averaged over, so risk neutral expectation over the next 22 days is given, so that is the VIX index. The on-off run United States 5-year spread, which provides a measure of liquidity in the market. So we have the VIX index, which is a risk neutrality as an assumption parameter over 22 trading day. We have 5-year spread, we have the swap rate, we have the repurchase rate spread, which is a measure of credit spreads, a measure of default risk for the United Kingdom, and the 3-month United Kingdom LIBOR rate spread. Consider the following dynamic structural model of YT. So beta naught YT, beta 1 YT minus 1, beta 2 YT minus 2, BK YT minus K. So this is the dynamic structural model. Remember, we are talking about structural GARCH, S-GARCH or S-VAR model, which is an alternative method for modeling multivariate GARCH. E is 0, utility transpose is D, utility transpose is 0 when T equals no, T not equals S, and this is our GARCH parameterization. And this is iterative. I0 want to create a matrix of structural parameters with beta naught having coefficients of unity down the main diagonal to represent the usual normalization. So beta naught has 1 down the main diagonal. K represent the order of lags. U is a vector of independent structural disturbances which separate GARCH one. So the each in U, in case of U, each vector has a separate GARCH. So the VAR with diagonal D is beta naught inverse, where we have ones down the main diagonal is the coefficient beta 1 divided by beta naught YT minus 1, beta 2 divided by beta naught YT minus 2, or this represents VAR, structural VAR, phi 1 YT minus 1. Okay, but the VAR parameters are related to structural parameter for all I, beta 2, good. And the VAR disturbances are UT by beta naught. Now U is, we have learned this before, U is basically Z by root over D. This is the diagonal element of the matrix. D is again UU transpose, which is basically the diagonal element of residual diagonal elements of residual. Z is the standardized residual or standardized structural shock. So we learned this before. We know D root over D by B naught is S. We learned that before. So this is the VAR disturbance. VAR disturbance have time varying covariance as is, so SS transpose is V. So basically SS transpose gives you V. This is all that we need to remember. Unlike structural disturbances, this matrix is not diagonal. Now V is not diagonal provided that beta naught and hence S are not diagonal. Because beta naught is not diagonal, from beta naught we get S, right, root over D by beta naught. Z is diagonal, but this is not a diagonal matrix V, SS transpose. About that beta naught S, which in case volatility of all factors has an effect. So you have a contemporaneous matrix, so where volatility of all factors have an effect on all other variables. The following short-run restrictions we can put, like we can just estimate beta 2, then beta 3, beta 4, beta 5, beta 2, beta 5, like that, beta 5, beta 6, beta 6, just the way we want. depending on effects, because each parameter means something, where global risk factor is there, narrow liquidity factor, broad liquidity factor, credit factor, default factor, idiosyncratic factor. Okay, so here idiosyncratic factor is unity. We get unity down the line in case of beta naught, and down the mean diagonal, and we can check for these effects. Notice all factors are designed to impact on the LIBOR rate as given by the last row. So last row is the LIBOR rate, where all factors will affect. So in other words, what are the other factors? One more time: VIX index, US 5-year spread, swap rate, repo rate, measure of default risk, so 3-month UK rate. VIX index, US something, what is US? VIX index, then on-off rate, measure of liquidity, US measure of liquidity, US measure of liquidity, exchange rate, measure of liquidity, then exchange rate. Interesting problem. Exchange rate, then comes repo, default risk, and LIBOR rate. Repo, default risk, and LIBOR rate. So US liquidity factor, swap, broad liquidity factor is the transfer. This is VIX index. The variance decompositions are given in for 1 period shock, 5 period, and 20 period shocks. These decompositions are time varying S, which is root over D by beta naught, is used to compute the orthogonalized impulse responses, which is time varying through the conditional variance matrix D. The results of 1 period variance decomposition over time for US LIBOR rate spread given in the first row shows that the key factors are idiosyncratic factor and broad liquidity factor. Idiosyncratic factor and the broad liquidity factor. In the first row of figure 20.8, the results of the 1 period variance decompositions over time. Key factors are broad period. Okay, so this is broad liquidity factors and idiosyncratic factors, 1 period, 5 period, and 20 period. Over the next 5 periods and 20 periods, the global risk factor progressively increases in importance. Does it? Global risk factor increasingly increases in importance. So yeah, global risk factor increased with shocks. So this is the problem, right? So let's see. Modeling LIBOR rate for time varying volatility, everything is there, 1, 5, and 20 period. And this is structural VAR, another way to model VAR. So LIBOR, is there any additional functions? Are we optimizing any function? Probably. So this is wrapper function for SVAR, B, and volatility V. So delta, unpack parameter vector, delta is 14 to 19. So how many is there? Let's first structurize the model. This is the restriction: 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13. So these are all the parameters with all the factors that we need to estimate. Which, let's go back to 38. So all these beta parameters must be estimated. Delta is from 14 to 19, delta, alpha, beta. Okay, so we have 5 variables. So we need to find delta, alpha, and beta. So this is beta naught, this is just beta naught. then we have to find delta, right? So now this time we need to find delta, alpha and beta. What is delta? Is constant, mean. Okay, fine, makes sense. Alpha and beta are coefficients. This is 44. Let's go to page 54. Estimate model interpret the factors. Okay, there is delta, the GARCH parameter. I'm sorry. So betas are represented, alpha and beta, 5, 5. So there will be, each factor will have a different GARCH. So that's why alpha and beta. So delta is squared because variance, yeah, squared. And then norm CDF, we always do the bound thing because we're dealing with volatility. So norm CDF, something we need to remember. Residual is inverse of this. So beta naught V transpose beta naught, right, is residual U. B transpose beta naught is U. Confusion? Let's go back. Okay, so beta naught U, V beta naught U by beta naught transpose. So U is beta, this beta naught inverse, and beta naught inverse V transpose. We take U here, beta naught inverse U transpose V residual. Okay, fine, I'm fine with that. Okay, not necessary. Transpose crosses out. So basically inverse of beta naught. For I equals 1 to t, if I equals 1, then d delta alpha squared, then this is that, else delta alpha u I minus 1 squared plus beta into d. If I equals 1, if I is, for the first one basically, alpha u square beta into d, alpha u square beta into d. So alpha u square beta into d, we get 44 and 54. Alpha u square beta into d. All right, yeah, makes sense. 44. Beta into d, because d is equal to delta plus alpha, because when we have GARCH 1 1, this is GARCH 1 1, standard deviation of u squared. When you have a multivariate model, 1 beta into d, this is how it looks like. It's updated automatically. Omega is beta inverse diagonal beta inverse, beta naught transpose. So beta naught transpose beta naught d diagonal. So this is it. This is omega. Okay, they are calling it omega. Beta into d. The GARCH equation, alpha beta sigma, so sigma square, right, u square sigma square d delta. This is t, but when in case of multivariate, multiply d, u square u I minus 1, you don't square it, u becomes I minus 1, because here you just have 1 u. Then this is omega, and then this is the function, and the log likelihood function looks like Yeah, this is just the regular log likelihood function. 4054, just the regular log likelihood function. Fine. Return matrix to compute time varying covariance. Get S matrix. Unpack, same unpacking, same thing, same restrictions, same equation before. This is something changing. Beta naught diagonal of square root d. S matrix. We are not getting S matrix here. Diagonal B inverse. But when we are getting S matrix, our small things change. And the small thing is here, which is beta naught diagonal of square root d. Beta naught square root d. There you go. S matrix. Beta naught square root d. Previously we were talking about this part, now we are talking about this part. So S now for I, Si, the vector, the matrix, I rows all columns, is vectorization of TMP. Now what is Vic? Vic is something, Vic is something else. Probably is a regular function here. Generate Vic model. Generate, okay, let's see. Vic model impulse responses. Vic 3 model autorecursive. So Vic to var, what is Vic? Generate impulse responses from this Vic 3 model. In other words, general impulse responses from vector error correction model. So this is Vic. Yeah, we can check though. Impulse responses are being generated from Vic model. There you go. Let's see, this has a different definition as we're calling this function here. Or for some reason the program has become very slow. So it seems Vic is also column stacking of matrix. So here what is happening? In I rows one column, column stacking TMP. Okay, in I rows for all. Okay, so this is for in a for loop for each vector actually, for each variable I'm column stacking. The whole thing here S is put into one column and contemporaneous relationship is captured. Reshape a matrix to agree with Gauss. So this is a reshaping command. Maybe we'll need that. YRC. Fine. Now let's have a look into the code. So input all the data, 6 variables. Dummy variables allow for structural break in volatility, which is zeros. Then dummy 913 to end is 1. In volatility, this period has 1. S var parameters, order of var lag, q lag. Exactly, we have done this before. Estimate var with p lags, trimmer, we studied that before. Well as estimate, just like before in chapter 14, in chapter 15, structural var model, construct L and var matrix, everything else. Reshape egg, okay, we used that before. Invert AI A1 for optimization. So we optimize, this time we optimize the matrix. So up until this var and well, let's estimate p lags, estimate the var, we estimated var, we construct autoregressive model A1 inverse A1. So up to this is from previous method. Then we optimize. After we optimize, we get B and V. Beta naught is estimated with optimization. Then beta naught and V, we get S. We gonna use S this time. Now vector moving average is estimated with the given S store. No, where is S store being used? Okay, now this is moving average parameter estimation. Construct orthogonalized impulse response. Now S is reshape egg, S store, which is the matrix with B and V, because beta naught and V, which is the matrix with B and V, size of V. So this matrix automatically gives me S basically when we run it. So what happens here is very simple. You have functions from this GARCH chapter that you put into this previous code that you had when you were doing variance decomposition. So S store is used. Up until this is everything old. Choose a point in time, store t date or t date, one row, all column kk. Impulse is vector of S transpose, because this is the S matrix for k rows, k columns. So S is a k by k. Here you go. And for 2 to q, TMP and impulse, just like before. And you do variance decomposition, you just use S store from your GARCH. That's all. So basically this is it. There is a bit more thing here for measure variance decomposition, graph the engine effect of shocks on LIBOR over time. So this is just graphing decomposition time, lag 1, lag 5, lag 20. We'll talk about it later if we have time. Up until now we end. We'll revise it one more time though. Thank you for your patience.